Okay, welcome to module number 15 regarding transportation materials. This is probably one of the more interesting modules relating to the current drivers of civil engineering, particularly amongst Toronto. Anybody who's taken the local transportation can understand to that. It's also one of the biggest emerging areas of civil engineering that has a very large demand. So there's quite a bit actually to cover in this module. It's a rather fun one. A little bit to go with is that we'll have a little bit of an introduction to transportation engineering and some of the drivers that are drivers, as pun intended, that are determining where the field is actually going from or going to. And then we'll talk a little about the materials that are used for transportation infrastructure. Kind of starting out, we'll talk actually about how steel is used and how some of those members come to be, but mostly we'll be talking about asphalt. But one of the things about this course that typically gets missed is this course is usually pitched upon the way of saying, okay, well, asphalt, 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 and that's the only transportation material that you'll encounter. But the reality is you're going to be utilizing novel materials to do very interesting types of designs, but even some of the materials that we've already covered, such as soils, steels, concretes, and even timbers. For the most part, it's important to actually see how all of this kind of feeds in. And as I mentioned, novel materials, there's materials that are being developed that have ways of ensuring more of the longevity of the structure. For example, if you were to consider concrete that would deteriorate or crack, there is self-healing concretes that are being developed, which are a very interesting application. Okay, to begin, I'm going to start talking about the San Francisco terminal that was more recently put together. What you're seeing in this photo is one of the Cast Connects systems that was utilized to make the pedestrian village on the top. These are some of the photos I took a couple of years ago. Unfortunately, I couldn't actually visit on the canopy or the park or the elevated park above it because it was closed, mostly because there was concern of a connection, not this connection, but another connection that had some of the structural engineers at the time very worried. This is another close-up shot. You can see the reason that they use the cast systems is because it does not have a weld. And because it doesn't have that welding action, you don't get that weak point where these members actually come together. Now, we've covered how Cast Connect systems were made in a previous lecture. So we're not going to really spend too much more time other than to illustrate that in this particular structure, which is considered a transportation hub, where all rails and all buses are all coming in, that this is one of the structures that needed to be, to facilitate this, needed to be constructed with steel. These are some photographs of showing that process. You can see the subway system, and then on the exterior landing, the bus drop off and pickup. And then also on the top of the building, a very nice parquet. You'll see if you visit the World Trade Center in New York, you'll see other very modern style of transportation hubs that are meant to have a large population come through each day. And you can see how integrated these steel sections actually are. Of course, in Toronto, there's some very impressive transportation infrastructure. This is a photograph of the Billy Bishop airport terminal. And one of the things that had to be done to facilitate this transportation structure was the construction of a tunnel that would go underneath of a riverway. So in this case, this is a tunnel system that has about a 10-meter diameter and actually is about a 200-meter length. To construct this really required a really good knowledge of soil conditions and as well as concrete. So basically, in this case, there was a rock mass that basically went through the structural system but there was a large risk of these rock masses actually falling and collapsing the tunnel under construction. So what happened was is a series of interlocking drift bores were created, and these were all backfilled with concrete so that they could basically make a series of arches throughout this tunnel to actually support it so it wouldn't fall down, and then bolting this into the existing rocks. So one of the things about this tunnel system is that there's basically the viewpoint of having about 1,000 pedestrians walking through this tunnel a day, which is a pretty impressive aspect. On Moodle, there are a few documents that you'll have access to that you can read through about the future of transportation. These are documents by the consultancy firm Arup that describe where it is our transportation infrastructure is going. You already know that within Toronto, there is a driver and a push to expand light rail, as well as people wanting to move subway systems. And the big driver between any of this transportation stuff is that the majority of the infrastructure in most communities was built up in the 1950s and into 1960s. In fact, if you go through some of the subway stations in Toronto, you'll see that these were constructed some time ago. And they get very crowded because there's urbanization occurring. That's a large mass of people moving to the center of the city. And it is in the case of that these population peaks may not have been foreseen decades ago. And we know that populations are going to keep increasing because of urbanization. Everybody wants to live in the center of the city, and therefore property prices are increasing, and a need for transportation to move people around is also being increased. And you can see this very visually in a video illustrating this in China. So have a look at this one and just see how much congestion is occurring in this roadway. Isn't that just... And you get the picture. Within these documents, you'll see that there's a number of new technologies that people are looking at. Photoluminescent pavements for smart and dynamic highways are a way of building up these structures. If you haven't heard of what photoluminescence is, it's a type of material and technology that basically absorbs light and then re-emits it in a sense of when it's dark. So it's kind of like your glow in the dark aspect. You'll see it in stairwells, particularly these are some illustrations. Some people are using plastic wastes in their roadway materials. We happen to use recycled concrete aggregates in road beds, particularly amongst the 401. And then, as I mentioned earlier, self-healing concrete. This one's really interesting because when the concrete cracks and water gets in, it activates the bacteria that's on the inside. And the activated bacteria on the inside begins to produce limestone as waste. So you can have this type of technology. And of course, multiple people have been forecasting where technology is going to be going, particularly for transportation systems. And there's a viewpoint that we're moving towards autonomous vehicleization. That's where you don't have drivers. And how far away that is commonly disputed amongst people, but it is a new way of looking at how roadways are going to be utilized. So very much interesting things. You'll find more details to these systems within the manual or the documents that I've posted themselves. Great. Okay, so now we're going to talk about asphalt. Asphalt is a very interesting material. Essentially, bituminous materials are classified as asphalts and tars. Asphalt is obtained from the petroleum, which is refined. It tends to be very sticky, highly viscous at room temperature, usually used for road pavements, repairs, sealings, and waterproofing. And essentially, when we're talking about asphalt cement, we're talking about a mixture of asphalt and aggregate. We no longer really use tar, but certainly this is a material that you may still come across. It's obtained from the coal production. It tends to be very brittle on cold days and flowing and fluid on hot days. In terms of asphalt concrete, it tends to be flexible pavement in a way. Tar, as I mentioned, was commonly used as a binder in pavement materials a long time ago, but it's not really used very often anymore because it ages and oxidizes more rapidly than asphalt will, so there's a shorter life to it. It's more sensitive to temperature, and also it's a class 1 carcinogen, and that's not good. So in terms of solubility, tar is not soluble in petroleum products. In cases where oil spills are expected, tars can be used as a binder, so that can be considered in a sense, but it's only really used for special applications. Asphalt cement is called paving asphalt. Asphalt binders, asphalt concrete, asphalt cement concrete, hot mix asphalt. These are all different names that you might come across that all mean the same thing. There are three different forms of asphalt used in pavements. One is asphalt cement, cutback asphalts, and asphalt emulsions. And basically, the production of asphalt cement is basically you heat it, you thin it, or you can have it as suspended in water. These are the three main types of asphalt that you might encounter. Asphalt cement is a combination of different aggregates that are heated, dried, combined with asphalt binder. The aggregates are held together in the sense of an asphalt binder. It's very similar to what you would see with concrete, only it's not cement now, it's a binder. Gradation is very important depending on how you're using it. Types of gradation used in pavement construction: open graded, there's large void space with little to no fine aggregates. Very good for drainage in open graded. Intermediate graded, usually used as a base course. There's large aggregates with some sand, but it's still permeable. Densely graded, well, it's well graded, made of coarse defined material, provides a dense and permeable layer, and that's usually used as surface course. Asphalt cement layers, if you're making a little roadway, you'll have a surface course, and that must be able to withstand wear and abrasion forces. And this will provide you stability to prevent surface from rutting. You'll have a base course. The choice of the base layer depends on the cost, the availability of materials, the traffic that's going to be used. It can be used either as open graded asphalt concrete or open graded Portland cement concrete slab, and both allow for drainage of water and structural support. The sub base is only if the subgrade soil does not possess suitable properties, so you might see that used. And then of course the subgrade is basically a natural soil, and that just basically acts as the foundation of the roadway itself. In terms of production, this one is a little bit tricky, and if you ever have a chance to see it, it's actually very impressive when they pour it, but it's also highly dangerous, which I'll talk about a little bit later. Basically a batch, it's dry and heated aggregate and blended aggregate and asphalt in a separate mixer, and it's always made one batch at a time. So first is there's a cold storage for aggregates, and there's pre-measured amounts of different size aggregates that will fall on a belt conveyor. Then there's the drying and heating of the aggregates, which is conveyed to a rotary dryer. And then collectors are to remove water vapors and dust from the drying process. The materials are then discharged from the dryer and travel up the hot elevator, and you can see that in picture 4. And then a screening is used that transfers the material to a screening unit, and the screen separates the materials into different sizes and rejects oversize. So it's kind of like your mixes, your concrete aggregate sieving process. Then you go through the weighing hoppers from the hot bins. There's scales to weigh off the controlled amounts of aggregates that you want. The Hosh asphalt binder, filler, and reclaimed asphalt pavement might be used to mix to a specific mix design. We won't talk about the mix designs in this course, but you should be aware of them. Paddle mixers then used, and the ingredients are emptied and combined into the paddle mixer until the contents are fully coated. And this is all going to be prescribed to a particular mix design, very similar to how a mix design in concrete is done. And then the discharge of the mixer loads directly into the waiting truck or temporary storage silos. Now, an alternative process is a continuous process, and this is done via a drum mixer, where the dry aggregates are blended with asphalt and in the same piece of equipment. You still have the cold aggregate storage with measured amounts pre-graded. You do an automatic weighing system, monitors the amount of aggregate flowing into the drum, and then you have the asphalt and aggregates thoroughly blended within the mixer, collectors to remove water vapors and dust from drying processes, and then a discharge. The mixture is discharged directly into temporary storage silos. And so these are some illustrations of the various technologies that you may encounter. In both processes, the hot mix asphalt is produced at the plant by drying, heating the aggregates, and then mixing and coating them with a warm liquid asphalt. In terms of the cutback procedure, this is produced by dissolving asphalt cement using solvents, gasoline or kerosene, to form a liquid product at low temperatures. And this allows for the easy placement of asphalt without using high temperature. The solvent gradually evaporates, leaving behind the asphalt binder. The disadvantages of cutbacks is that you're releasing volatile petroleum fumes into the atmosphere. And this adds to air pollution, and these vapors are very potentially flammable and toxic. When you talk about flammability, if you think back of some of the previous conversations I've had about high temperatures, whenever you have a gas mixing with oxygen and you have the right amount of heat, that can produce a fire. So you have to be careful. Cutbacks and emulsions, which I'll cover shortly, are used for the same applications, but because of the environmental impact, you'll see cutbacks used a lot less. In emulsions, the asphalt is mixed into water containing an emulsifying agent, such as soap. It contains about 70% asphalt, 30% water, and some small amounts of emulsifying agents. Think soap, for example. Water evaporates, allowing the asphalt globs to come together to form a binder, and the residual asphalt retains all the adhesion, durability, and water resistance from which it was produced. This is good when aggregates are in the dry, damp, or wet states. There's no toxicity or fire direct issues. It can be mixed without any application of heat. And this is a more specific example of emulsified asphalt to describe the process. Whereas the water is in a continuous phase, the asphalt is just in a dispersed phase. And basically, the emulsion is a suspension of small globules of one liquid in a second liquid, in which the first will not mix. Think of it like oil and vinegar, for example, like salad dressings and things like that. That's a good way of looking at it. And that's basically asphalt. Now, one of the big problems that you find with infrastructure is, of course, with time, it degrades and it has a service life. So what happens is, through various mechanisms, it is going to have some damage. So basically, over time, there's an oxidization. It becomes brittle. Fresh asphalt is usually black in color. It's turning gray as it oxidizes and ages. And the asphalt can be very prone to cracking at low temperatures. Liquid asphalts are usually used to extend the service life of pavement. But what you'll have a necessity to actually fix some of these surfaces, and you have a choice and a range, which are very much dependent on pricing. So for example, fog seals, chip seals, slurry seals, microsurfacing, crack sealing, and tack coats. And they all cost a different amount to actually make. A fog seal is generally a light application of diluted asphalt emulsion to the surface of an oxidized pavement surface. Fog seals are generally very low cost, and they're used to waterproof and restore flexibility of a hot mix asphalt surface. Usually only lasts 1 to 2 years, so it's great for politicians before becoming elected. Looks like they're doing something. Minor sealants, it generally cannot fill anything larger than a hairline crack. Retards oxidization in this sense. And you can get a viewpoint as to what something looks like with and what something looks like without with this. A chip seal is a high viscosity emulsified asphalt surface, which is incorporating rolled in rock chips over existing asphalt concrete pavement. The liquid asphalt emulsion is followed by an aggregate chip coating, and this seals cracks in the pavement from water and debris, so it provides some waterproofing. It gives you some surface friction. It's non-structural, no rut filling capacity. I'll talk about ruts shortly. And this lasts about 3 to 6 years. So it's a bit better technology than the one you just saw. A slurry seal is a mixture of an emulsified asphalt, which is well graded. That's fine aggregate, sand, and mineral filler. And this is used to fill cracks and voids and gives a new surface to the pavement. It's used in light traffic roadways. It seals the pavement from water and debris, seals small cracks. It's non-structural, lasts about 3 to 5 years. And opposed to the fog seal or slurry seal, it contains aggregate and can therefore correct minor surface defects and fill in cracks and voids. So this one's a really good one in that sense. If you have a lot of money, you can do microsurfacing, which is a slurry seal with advanced polymer additives. And these are used to preserve existing pavements. And these are used generally for moderate to heavy volume traffic. It's using a polymer modified asphalt emulsion and an aggregate in Portland cement. And these last about 7 years. They seal pavements for water and debris. They're still non-structural, but they can fill ruts and correct pavement slopes. So that's a very good advantage. It's just they're incredibly expensive. And of course, crack sealing is one of the things that you'll see that are done on some roadways, particularly those that have been overloaded. They're used to fill individual pavement cracks to prevent the entry of water, sand, dirt, or rocks. These were heavily used in the 1980s for repair. In my view, they don't really have very long durability. They generally only last 1 to 2 years, and they're used for cracks under half an inch wide. They're very easy to just pull off the roadway as well, so they're not the best system. A tack coat consists of an emulsified asphalt. It's applied to an existing surface to provide a bond between the new construction overlay and the existing surface. So this is between the asphalt and the base course, or the base course and the sub-base, as you can see. And you can see in these illustrations how this would actually look. There's a nice table in your textbook that describes the pavement applications of asphalts from description to application. In the past, I would ask, at least with the written version of the exam, to fill in a very similar table. So I would expect some level of memorization of this table. As I mentioned before, I would describe rutting. Rutting is basically depressions which develop in the wheel tracks of asphalt pavement. So you see if you have the loading going over and over and over, eventually creates a rut in the surface. It basically results in the deformation of pavement layers or subgrade, which are caused by movement of the materials from the traffic loading. And this is usually due to insufficient compaction or poor mix design. In antiquity, in roadways, you would see rutting, but it's not because of the deformation of the subgrade layers. It has to do with the deterioration of the rocks themselves under constant loading conditions. About ½ inch deep can usually be left untreated, but more so it would require treatment. In terms of thermal cracking, results from shrinkage of hot mix asphalt due to low temperatures or asphalt binder hardening, and this will actually allow water infiltration into the subgrade or subbase. These tend to be, if it's small, less than half an inch, a crack seal can be used to prevent entry of moisture. If it's large and numerous cracks, you might have to remove and replace that technology. Fatigue cracking is caused by repeated traffic loading. So basically on off, that's what fatigue is. It's consistent loading and unloading. The cracks connect, forming small blocks that develop into a pattern resembling the back of an alligator. And these are due to heavier loads than anticipated in design, or inadequate compaction, or the loss of a subbase or subcomponent support. And the repair to this is to remove the cracked pavement, replace the poor subgrade and patch, or if it's a large area, place a strong overlay to carry the load over the entire pavement surface. We've talked a little bit about that with the movement of the house. When the house is being moved, it was putting a large weight on the surface of the roadway, so they needed to put steel plates out to distribute the load evenly so it wouldn't break the roadway itself. I think an excellent question on an exam would be a series of photos showing these different types of deteriorations, and then identifying what is actually going on with these deteriorations, what caused them, and how do you fix them. You can learn about mix designs in this image, in this document, the Marshall mix design. That tends to do that. There are other types as well. So if you took a more advanced class on transportation, you would learn how to do the actual mix design itself. Okay, this is usually just a little slide of just a little fair warning about the dangers of working. Most of you will probably take a job over the summer in a very construction oriented area. That's usually tends to be the second year jobs. When we talk about lab safety is brought up a lot in the materials course, and we say, oh, you need to wear steel toe shoes, you need to wear a hard hat, you need to wear safety specs, and there's always like 3 or 4 people who aren't really paying attention to safety, and who don't wear the materials and don't take it seriously. And when you get out into the construction site, it is really, really important to take these things critically. So a while back, there was a construction site that was going on, and it was delivering asphalt to a site, and the truck itself was dumping the asphalt, but the asphalt got stuck. And one of the summer students decided, well, if it's stuck, I'm just going to prod it, and then eventually that will release it. The problem is when this junior student was prodding it, it triggered the whole thing to come out. It didn't come out slowly. All of the asphalt started to come down, and it basically fell all on top of him, and essentially burying him. And of course, all the other workers were trying to, recover him right after all this mix fell on him. Now, the temperature of this mix is about 200 degrees Celsius or so. So this individual sustained very severe burns and eventually is asphyxiated. Now, the real trauma to this, apart from the life loss, was the legal aspect, as to the parents of the student ended up suing the construction company. And the settlement that was made based on this individual, and the fine to the company was only $33,500, which I find extraordinarily shocking, because that just basically is peanuts. But essentially that was the grim tale of about what the life loss was. And it's really important when you go out there that you're thinking about your own safety when it comes to PPE, or even what you're doing on the site. And of course, if you do not feel safe, you do not have to do the actions Nobody can force you to do something that's not that you feel is unsafe. You have those certain rights. So it's extraordinarily important to learn what those rights are, so that that you know what you can and can't do. Because at the end of the day, if you are hurt, there isn't going to be somebody really helping in that sense all the time. So I think it's really important to think about that, particularly if you do field work, moving forward in your careers. And certainly some of you are going to encounter some very shocking things if you're not careful. Okay, so that it's not a very long module, but it is important to go through some key things to really be thinking about. Again, the transportation engineering, you have some readings from this module. You should have a look at those. I think you'll find them very inspiring. There's a lot of technology being talked about. Transportation materials are so much more than just asphalt. Of course, it is a big component, but there's so much more going on. So make sure that you're familiar with the different types. I think the repair technologies are the more critical ones, about how are you going to actually repair something if you see certain types of damage states. And I think that would make an excellent exam style question. Beyond that, like I said, have a look at those documents and go through those materials. Be careful with your summer jobs. These are dangerous materials if they're not cared for correctly, and you can get seriously injured in many cases. Okay, so we're going to end this module here. Thank you very much for your attention.